Hello, everyone. Welcome to a new lecture of our course on processing in memory. Today, we have another interesting research talk by Geraldo Francisco de Oliveira, who is a PhD student in the Safari Research Group. As you may know, he already delivered 2 lectures in this current edition of the course. In the last lecture, last Thursday, he talked about SIMDRAM, a framework for SIMD operations using DRAM, and today is going to switch gears to something different. He will go back to processing near memory architectures, but other types of specialized accelerators as well for machine learning inference workloads. So thank you very much, Geraldo, for delivering this lecture. Feel free to start whenever you're ready.
Thanks a lot, Juan. Thanks for the introduction. So welcome everyone again in this processing in memory PNS class. And the following 2 lectures are going to be about hardware software co-design for a specific workload using processing memory techniques. So you're going to see how we conduct this type of research in our group and how processing memory can be used to accelerate different data-intensive modern applications. So today we are going to talk about machine learning, and particularly this paper was published in PACT last year and was led by Oliveira, which is now at Google. He did his work while he and I were at Google doing an internship. And the title of the paper is called Google Neural Network Models for Edge Devices, Analyzing and Mitigating Machine Learning Inference Bottlenecks. So before we start, I'm going to give an executive summary of what this talk is about. So in this work, we extensively analyze state-of-the-art machine learning accelerator, which was the Google Edge TPU, using 24 different Google Edge models that are commonly used across many different products within Google. And those models include CNNs, LSTMs, transducers, and RCNNs. And we identified 3 key problems from that the Edge TPU accelerator suffers from when executing those different models. So the first one is that it operates significantly below its peak throughput. The second one is that it operates significantly below its theoretical energy efficiency, and also that the memory hierarchy was leading to some particular bottlenecks. So it was quite inefficient for some of those models. So the key insight that we got for all of these analyses for all of those different models is that the main problem arises because the Google Edge CPU is designed as a monolithic accelerator with a on-site fit-all type of design, and does not cater for the heterogeneity that we see across those machine learning layers or those neural network layers, and that leads to different design decisions that would be optimal for the accelerator. So based on that, we propose a framework which is called Mensa, which consists of a heterogeneous accelerators whose both data flow and hardware design are specialized for a particular family, what we call families of layers. So those are pretty much layers within a neural network model that all follows a similar set of characteristics. And those characteristics drive the design of the accelerator. So we use this framework to propose Mensa G, which is a version of Mensa for those 24 Google Neural Network edge models. And we see that Mensa G improves performance and energy efficiency by 3 times and 3.1 times compared to the baseline Edge CPU accelerator, and also reduces the cost and then improves the area efficiency of the overall system. So here's the outline for this talk. So first, I'm going to give a brief introduction of edge accelerators and machine learning models. Then I'm going to give our extensive analysis of the edge TPU and also on the machine learning models. Then describe the Mensa framework, describe our design of the implementation of the Mensa framework for the Google Edge models, then evaluation and conclusion. Feel free to ask any question in the YouTube chat. I'll be glad to take them. So we start with the introduction. So there is a large interest recently in executing machine learning tests directly on edge devices on opposing to send them to the cloud. And there are a couple of reasons for that. So the first one is because it's much better for privacy in the private perspective because the data is local to the device. The second one, it allows to run machine learning inference even if you don't have internet connectivity. The second one, it enables you to have much faster latencies because you don't need to go through the internet connection to the cloud. And so it reduces that particular communication latency, which is key for many tasks, as for example, for autonomous car that has a really timely deadline for the model to respond to. And also in terms of bandwidth, because you are no longer limited by the network bandwidth. But there is this problem because edge devices are pretty limited in terms of power budget and computational resources. And as a result, it's very challenging to execute resource-intensive machine learning tests directly on them. Because of that, many players in the industry have decided to design their specialized edge-based ML models to particularly run inference. So here in this slide, we have the example of the Apple Neural Engine A12, and also the Google HTPU, which is going to be the target of our studies. So at the same time, neural networks are evolving quite rapidly. And right now we have a sea of different machine learning models, and each model is tailored for a different type of application or task. So the major challenge right now is how can you design an edge accelerator that can efficiently execute inference across all of these different machine learning models. Next, I'm going to describe our analysis of those various neural network models that are employed within Google, executing on the HTPU accelerator. So we analyze the Google Edge models using the Google HTPU as the baseline accelerator, and the HTPU is not much different from other proposals related to accelerators for neural networks. So it's basically a historic. The HTPU is basically a historic array accelerator, which is a generic tile architecture, which here I'm going to give a brief overview of how it works. So the ML model in the HTPU is first stored in DRAM, and then the model is fetched from DRAM by the accelerator layer by layer. So each layer includes parameters, which can be input or output data, and also activation, which are the pre-trained weights for the particular model and for the particular layer. At a high level, the accelerator has 4 key components. So it has a processing element array to perform multiply and accumulate operations. In the HTPU, we have a 64 by 64 array that can achieve a peak throughput of 2 teraflops per second. We also have on-chip buffers to hold parameters and activations. And also we have so we have 2 things, 1 chip buffers, one for parameter and another one for the activation. And fourth, we have a data flow that specifies how parameters and activations are mapped to the process element arrays and move the movement between those the buffers. So we analyzed the inference execution of the accelerators using 24 different machine learning models that are used inside Google, as I said. So those models are the following. So we analyzed 6 RNN transducers, which are used for applications such as speech recognition, 13 convolution neural networks or CNNs, which are usually used for image classification and object detection, 2 long short-term memories or LSTMs, which are used for application as language translation or handwriting recognition, and 3 recurrent convolution neural networks, which are a hybrid between RNNs and CNNs, used for applications such as image captioning. So we found the 3 main challenges faced by the HTPU accelerator when executing those 24 different machine learning models. So the accelerator operates significantly below its peak throughput, operates significantly below its peak energy efficiency, and handles memory as access quite inefficiently. So I'm going to go into more details about each one of those challenges next, starting with the problem that it leads to low low utilization from the accelerator itself, leading to low throughput. So the key problem here is that the accelerator operates below its peak throughput during inference. To illustrate such an issue, we rely on a roofline model, where a roofline model is a common model used to identify bottlenecks in a system, and the model has a x-axis where we show the arithmetic intensity of a particular network layer in flops per byte, and the y-axis we have the achieved throughput for that particular layer in teraflops per second. And the peak throughput of the HTTP accelerator, as I said, is 2 teraflops per second. So we make two observations from this plot. First, we observe that the transducers and LSTM networks have the greatest underutilization, with both achieving less than 1% of the peak throughput of the HTTP accelerator. And second, even though CNNs and RCNNs do somehow better than the LSTMs and transducers, achieving 52% of the peak throughput of the HTTP accelerator, this is still way below the maximum throughput that the accelerator can provide for neural network inference. Second, we observed that the HTTP accelerator operates far below its theoretical maximum energy efficiency. Again, here we have a roofline model to illustrate such an issue. This time around, the y-axis shows the energy of different models while executing inference on the HTTP in teraflops per joule. So the peak energy efficiency of the accelerator is of 1.42 teraflops per joule. And you're going to make two observations based on the analysis. So first, the energy efficiency is particularly low, is around 33% for LSTMs and transducers. And second, even the best CNN models only achieve 50.7% of the maximum energy efficiency of the accelerator. So third, we observed that the memory hierarchy of the HTPU is not efficient. To illustrate such observation, we use this figure here. In the x-axis, we have different neural network models, and the y-axis, we have the normalized energy efficiency for that inference execution and breakdown for different components of the accelerator, including DRAM, parameter buffers, and network on chips, of chip interconnection, processing elements array, buffer, activation buffers, and the static energy that the accelerator spends. So from the figure, we observe that 46% of the total energy for those models goes for the off-chip traffic to DRAM, and 31% of the total energy consumption goes to distributing parameters across processing element arrays. So after identifying such a challenge faced by the HTTP accelerator, the next question is where the challenges are coming from. So to answer this question, we go and do a further analysis on the models themselves to see the key sources of inefficiency that faced by the HTTP accelerator. So we draw two insights from our model analysis. The first one is that we observe that there is a large variation in terms of layer characteristics across different models. To illustrate, here we have a figure that shows the total parameter footprint for different layers and the float per byte reuse across different layers for representative CNNs, LSTMs, and transducers. So you observe from the figure that layers from LSTMs and transducers have large parameter footprints, while and lower users, while CNNs present the opposite behavior. They have not so large parameter footprints, but they have really high float per byte ratios. Second, even within a single model, layers show quite a large variation in terms of characteristics. So, for example, we take CNN as an example here, and we see across different layers in the x-axis how the number of MAC multiply and accumulate operations varies for those different layers. And we see that from one particular neural network model, the MAC intensity varies for up to 200 times across different layers. And we take another layer and we also see variation in terms of float per byte for CNNs across different layers. In this case, in this example here, up to 244 times across different layers. So the main conclusion from our analysis is that the key components of the edge TPU are oblivious to the layer heterogeneities of different neural network models, and even within a single neural network model. The monolithic design approach of the edge TPU leads to inefficiency and resource underutilization, since the accelerator design over-provision the size of the processing element arrays and the on-chip buffers, while assuming a rigid data flows and fixed off-chip memory bandwidth. This all leads to the three accelerator challenge related to performance, energy, and memory we identify in your analysis of the edge TPU accelerator. Next, I will describe a proposal to cope with such issues, which is our Mensa framework. So based on our analysis and insights, the goal of our work to design an edge neural network accelerator that can efficiently run inference across varying numbers of different models and layers. To this end, instead of designing a monolithic accelerator, we propose Mensa, a new accelerator framework for neural network inference. So in a baseline system, different machine learning models are executed in a single monolithic edge accelerator, which leads to performance and energy issues. On the other hand, Mensa distributes the layers from a neural network model using a runtime scheduler across a collection of smaller accelerators, which have been tailored for different properties of different layers. By specializing each accelerator to a subset of layers, Mensa avoids the shortcomings of current monolithic edge machine learning accelerators, resulting in a highly efficient and high-performance accelerator at the same time with a much smaller collective area, system area overall. So next, I'm going to briefly introduce the Mensa runtime scheduler. The goal of Mensa software runtime scheduler is to identify which accelerator a particular layer in a neural network models should run on. So it works as follows. So the accelerator gets a neural network model as input. It also has two other pieces of information: the accelerator characteristics and also the characteristics of each layer that are going to run during the inferencing execution. As I'm going to show next, different layers from different models tends to group into smaller families of layers, which share key properties and allows all of those layers to share a single accelerators. So in this way, we can have a small pool of edge accelerators where each accelerator caters to a specific family of layers. So we collect the characteristics on the accelerators and layers once prior to the inference execution. And with all of this information, the scheduler generates a per layer mapping between the layers and the accelerators by utilizing a specialized mapping heuristics tailored particularly for Mensa. So I invite you to check our paper for more information about the Mensa scheduler and Mensa runtime heuristics. So next, we highlight how our Mensa framework can be employed for a large set of neural network models, particularly those 24 neural network models that are run by the Google Edge TPU. So first, we need to decide how many accelerators we are going to need to have in our Mensa realization based on the key characteristics of the neural network models. We make a key observation that the majority of the layers we target fall into 5 major families in terms of key characteristics that impact the hardware design. So first, we find that 2 families of layers 1 and 2, that have low parameter footprint and high data reuse and MAC intensity. We call such a layers compute-centric layers. Second, we find 3 families of layers, families 3, 4, and 5, that have high parameter footprint, low data reuse, and low data MAC intensity. We call such a layers data-centric layers. Based on the key characteristics of the 24 neural network models and their layers, we designed 3 specialized accelerators: Pascal, Pavlov, and Jacquard. I'm going to briefly give an overview about the hardware characteristics of each one of those accelerators. So here is Pascal. Pascal is a compute-centric accelerator that is designed for the compute-centric layers of families 1 and 2. It has a 32 by 32 processing element array, since layers for family 1 and 2 have a large number of execute a large number of Mac operations. So we want to size the Pascal processing element array to efficiently perform those in parallel. We reduce the size of the activation buffer in Pascal compared to the baseline HTTP accelerator from 2 megabytes to 256 kilobytes. This reduction is possible due to our specialized data flow that we specially designed for Pascal. We also reduce the size of the parameter buffer from 4 megabytes in the HTTPU to 128 kilobytes in Pascal, because layers in families 1 and 2 have a small parameter footprint. Give the low off-chip memory bandwidth requirements for Pascal, we keep the accelerator on the CPU die. So next we have Pavlov. So Pavlov caters for layers in families 3, which are data-centric and mainly consist of data-centric LSTM layers. Because family 3 have pretty low MAC intensity and mainly performs metric vector multiplications, we design a much smaller processing element array for Pavlov compared to both Pascal and the baseline Google HTTP. So empirically chose a 8x8 array size to balance both latency and utilization. So due to a small activation footprint of layers in families 3, we use a 128 kilobyte buffer for parameters, while our data flow design for Pavlov allow us to completely eliminate the parameter buffer and stream parameters directly from the RAM. We decided to place Pavlov inside the memory, so it's a processing near memory accelerator to accommodate the large off-chip memory bandwidth requirements for family 3 layers. So here we are using a 3D stack organization for memory, similar to a HBM or a HMC design. So you're just taking Pavlov and placing the logic layer of such 3D stack-based accelerator. So finally, we have Jacquard, which caters for layers in families 4 and 5. Those are primarily non-LSTM data-centric layers. So while layers in families 4 and 5 have low MAC intensity, they perform a little bit more MAC operations on average than layers in families in family 3. Because of that, we empirically chose a 16 by 16 processing element arrays in Jacquard. We also use a 128 kilobyte buffer for activation and 128 parameter buffers in Jacquard. Similar to Pavlov, we place Jacquard inside the memory due to high memory bandwidth demands for layers in families 4 and 5. So we invite you to check our paper for more details on all of those accelerators, including the discussion of our specialized data flows for each one of them. Finally, we provide a brief overview of our evaluations. So we analyze the inference energy of our Mensa G proposal against a baseline HTTP accelerator, the baseline HTTP using a high bandwidth off-chip memory device as its main memory. And here in this plot, values are energy values are normalized to the baseline HTTP accelerators. And again, we break down the energy values between each component of the accelerator design. So we make the following observations based on our energy analysis. So first, Mensa G placement of the accelerators and careful data flow design enable us to reduce the energy consumed by on-chip and off-chip parameters by 15.3 times on average compared to the baseline HTTP accelerator. Second, Mensa G reduces the dynamic energy of on-chip parameters and network on chips by almost 50 times compared to the baseline systems with high bandwidth memory. We conclude that Mensa G reduces energy by 66 times, and improve energy efficiency by 3 times compared to the baseline HTTP accelerator. So we also analyzed Mensa G's throughput compared to the baseline HTTP accelerator and the baseline HTTP accelerator with high bandwidth memory. So we observed that Mensa G improves throughput compared to the baseline HTTP accelerator by 3.1 times on average across all of those different models. We invite you to check our paper for more details on Mensa's runtime scheduler or accelerator's data flow, a comparison against a prior state-of-the-art ad neural network accelerator, Mensa G's utilization results, and also Mensa G's inference latency results. All of that again is in our paper. Next, I'm going to conclude our talk. So in this work, we extensively analyzed 24 state-of-the-art machine learning models, edge machine learning models that are used within Google. Those models varies between CNNs, LSTMs, transducers, and RCNNs. So based on this analysis, we identified that the HTTP accelerator suffers from three main challenges. First, it operates significantly below its peak throughput. Second, it operates significantly below its theoretical energy efficiency. And third, is it inefficiently handles memory accesses. So the key insight from our analysis is that all of the shortcomings are coming from the fact that the HTTP accelerator uses a one-size-fits-all monolithic design for the HTTP. Which does not cater for the layer heterogeneity and model heterogeneity for all of those neural network models. So based on that, we propose a new framework called Mensa, and which basically consists of a heterogeneous set of accelerators whose data flow and hardware design are specialized for particular properties for different neural network models and layers. So we extensively evaluate Mensa for those 24 Google Edge models, and we see that the Mensa improves performance and energy by 3 times and 3.1 times, and also reduces cost and improves area efficiency. So thanks a lot for listening. I'm happy to take any further question, and we invite you to check our back paper in details through this QR code in the screen. Thanks a lot.
Very good. Thank you very much, Geraldo. Very efficient.
Thanks, Juan. That's quite short talk.
There are no questions in the chat. However, I would like to ask you a couple of things, some questions that came to my mind while I was listening to you. So the first one relates to the roofline models that you presented. It's a pretty simple question. There is a single dot per neural network model, right?
Yes.
And I assume so here it seems that you guys tested like 13, for example, 13 different CNNs. But inside these CNN, there are different layers as well, right?
Yes.
And these different layers have different characteristics. So just to clarify, the results in this slide correspond to kind of an average for the whole network, the whole model, I assume.
Yeah, this is correct. It's for the whole model, for the end-to-end execution of the model. So this particular plot is not broke down per layer. But internally, we did, this is basically for graphic representation, right? Because each one of those models have tens of layers. So plot them for a presentation would be quite crowded and hard to draw the needed insight. So this is an oversimplification of the model. When we were doing the analysis, we did plot both roofline models per layer, but then it becomes quite a extensive plot.
Okay, yeah, that makes sense. In the next slide, I'm curious the energy efficiency, right? I mean, I think that this is a really cool plot that is energy-based, or more than energy-based, like energy efficiency, right? Or performance per energy roofline model. So why? So here the roofs themselves don't, are not so straight, right? So there is no need curve there.
Yeah. So we took this roofline model. There is a paper that actually proposes this energy-based roofline model. I don't recall exactly the name of the title of the paper, so I'm not going to try to cite over here, but it's citing our work. And they specify over there in the model that is differently from the performance model. We don't have a need because different than the other plot, the energy can never be zero, right? For a system, you all have a static component and also a dynamic component, right? So even though the dynamic component can be zero, the static can never be zero. So this is why we don't have a knee point in the plot. is a continuous curve instead.
I see. Okay, that makes sense. So one more question with respect to the roofline models is, so for example, for the CNNs, did you guys test that, like, let's say, what batch size did you test here? Because I think that also the behavior in terms of memory or compute boundedness changes a lot depending on the batch size, right?
Yeah, I don't remember exactly which were the values of batch size, but it was larger than one. So this I'm pretty sure. The 128 number comes on top of my head. I don't exactly remember if it was exactly that for all of the models, but was not one, because we know, right, that there are some particular neural network models that or systems that do require to run batch one size inference, and then we see different results and leads to a different type of hardware organization in that particular case, right?
Yeah, exactly. Yeah, I thought about that, for example, when you mentioned latency for self-driving cars.
Yeah. In that case, it's a little bit different. But those ones here, I don't recall exactly, but yeah, it was whatever, because like all of those models were used in Google products, right? And they have like a predefined, let's say, command execution line, and we took them. We didn't question them much, because that was the premises, right? Those accelerators going to be placed in your Google Pixel phone, and it's going to run whatever makes sense for that particular application.
Yeah, I think that's pretty interesting as well, right? Because also the batch size might influence what's going to be the most desirable accelerator for a specific layer.
Because reuse, change, all those type of things, right? Yeah.
Okay, yeah, sounds very good. I have maybe a couple more questions. So there is something in slide 34 where you showed, I think it's energy results, the breakdown of energy results.
This one.
Yeah. So here, I mean, if I'm not wrong, I think you explained that there is a significant reduction in the energy due to the parameter buffer, the network on chip, and the off-chip interconnect. But I also see a reduction in the DRAM energy.
Yeah, it's true. So the main reduction is because the fact that two of the accelerators are placed inside memory, right? So this is DRAM. So both the DRAM traffic, but I think this component is more visible in the off-chip interconnect. But there is also the fact that we have a specialized data flow that is tailored to, once the data is in the processing element, to reuse it as much as possible for the layers that make sense. So then you don't fetch so much for DRAM. So there is a particular technique that we use, that like every time that is to reuse the data that they are placed in the register of the processing element array. So we try to reuse that value as much as possible. So based on that, we don't need to fetch so much from DRAM. So there is also that point.
I see.
Yeah, the data flow design helps a lot, because we can all of the data movement in those accelerators or in those inference models are quite easy to predict, right? Because we have the parameters predefined, the computation patterns predefined, everything is known beforehand. So we can optimize the data movement for that particular family of layers quite well, and then exploit whatever locality or reuse as much as possible for all of the accelerators.
Okay, yeah, that makes sense. Yeah, I wonder whether the performance of the baseline and the baseline with the high bandwidth memory could also change in some way, or significantly change with the this tailored data flow or this custom data flow for Mensa?
Yeah, we didn't do this analysis. We don't have this analysis, but I think it would definitely have some improvement. The problem there is just like how to change the data flow on the fly, right? Or like, because this data flow is quite predefined. So there is that challenge also, but like in simulators and stuff, you can definitely evaluate that for sure. And probably would benefit because the design itself of the hardware components are not so much different, right? Other than the process, the near data fact that we are leveraging high bandwidth DRAM when you go inside memory. But like the organization is pretty much the same. You have a systolic array that's fetching data from memory and like executing back operations, right? So I believe that probably even the baseline edge TPU accelerator could benefit for such specialized data flows.
Okay, so I think you didn't mention much about the heuristics, but I think it's also good to ask you something about the heuristics. I assume that, I mean, I don't assume, I know that it's in the paper. The heuristics also take into account the possible data movement across layers. What would happen if you switch, let's say, layer 1 to layer 2, go to different accelerators? That will entail some data movement, and the heuristics takes that into account, right?
Yes. So the heuristics is quite a greedy one, and we acknowledge that in the paper. That might be not the best possible heuristics, but what the heuristic basically tries to do is because is a kind of a software pass, and we know the structure of the layers, right? So we see how much I'm going to have to change from one layer to another, from one accelerator to another, and the communication that is going to require during the execution of their neural network. And then we have a threshold value, and that was empirically designed for those particular neural network models. And if the value if the data movement between accelerators is larger than this threshold, we decide to place the layer in one of the layers in it's not, let's say, not ideal accelerator. So even though that particular layer is not going to have that best performance possible because it's not placed in that best accelerator, overall you still improve the energy efficiency and the throughput of the whole system because you are avoiding this data movement. So there is this factor they take into account, and there is a footnote in the paper that we saw that on average accelerators layers don't shift much within a single model. Layers don't shift much between don't need to shift much between different accelerators. I think on average we saw that it needs to change 5 times or something, but like you have to think that one of those models have tens of 20s of layers, many layers. So some of them has 100 of layers. So changing 5 times is fine.
Okay, yeah, I think that sounds good. Yeah, I have a last one, and I think that this is kind of an obvious question. Is I assume that when designing this sort of framework and trying to propose specialized accelerators for the different types of layers, in the end you also have to make the decision of how many accelerators to use, right? And that's why, so it makes sense to cluster the layers into families, and it also makes sense to try to put these families together when and it's the same type of accelerator if they have some common characteristics, right? So, but and then you decided to go for 3 accelerators, and I think it makes sense if we look at the plots with these clusters of families. I think it's kind of reasonable due to the arithmetic intensity that the different families have. But how good have the performance or energy efficiency improved if in any if that would happen for if you have more accelerators, let's say 5, let's say 1 per family?
So that so the problem in that case is that we had like a kind of area budget, right? So we didn't want to be more costly than the baseline accelerator itself. So we try to reuse resources as much as possible, right? So if you have 5, so what I suppose that would happen is that at least energy, the static energy would be higher than the 3 baseline accelerators, right? So even if you propagate one of them, propagating still have a cost. um, and overall that would adds up for the total energy of the system. So would not be ideal. So it's really important to try to minimize the number of accelerators as much as possible when tailored for energy. In terms of throughput, maybe the throughput will be higher because you have just more processing element arrays in the end, right, or more hardware itself. But for in terms of energy and edge devices are quite energy power sensitive, it's really important to take down as much as possible and have a slim system, so we are not killed by static energy of having a hardware sitting doing nothing.
Mm-hmm. Yeah, I think it makes perfect sense. Of course, it's necessary to assume some trade-offs in the design of the accelerator.
So today I'm going to continue talking about how to do hardware software co-design to accelerate data-intensive applications. Last week we saw a case with machine learning, particularly neural network inference for edge computing. And today we are going to talk to the other spectrum of that of the computing environments. We are going to the cloud, and then we are going to talk about how to use process memories to accelerate hybrid transaction and analytical databases. So before I start, so this work was led by Oliveira, who is now at Google. So before we start, I'm going to give a briefly summary of what this talk is about. So many applications today need to perform real-time data analysis using what we call a hybrid transactional and analytical processing system, or HTAP. And an ideal HTAP system should have at least 3 key properties. So should provide at least 3 properties, which are should provide high data freshness and data consistency, workload-specific optimization, and performance isolation. We extensively evaluate state-of-the-art HTAP systems, and we see that they fail to provide all of those 3 HTAP properties at the same time. Therefore, our key idea to solve this issue is to divide the HTAP system into 2 isolated process islands, one for transactional workloads and another one for analytical workloads. Each island is occupied with a set of optimized hardware resources and algorithms. So by enabling processing islands, we can perform workload-specific optimizations to transactional and analytical workloads while providing performance isolation. So we leverage our key idea to design Polynesia, which is a novel hardware software cooperative design for in-memory HTAP databases. So we implement custom algorithms and hardware in Polynesia to reduce the cost of maintaining data freshness and data consistency in HTAP systems. And we exploit processing memory for the design of the analytical processing islands to alleviate the cost of data movement. We extensively evaluate Polynesia against 3 state-of-the-art HTAP systems, and we observe that it increases transactional analytical throughput by 1.7 times and 3.7 times on average, and also reduces energy consumption by 48% on average. So here's the outline for this talk. So first, I'm going to give a brief introduction about HTAP systems. Then I'm going to talk about the limitations of current HTAP systems, which is going to motivate Polynesia, then I'm going to give Polynesia a high-level overview of Polynesia, and then talk in details about Polynesia's update propagation mechanisms, consistent mechanisms, and also the analytical engine. Then I'm going to give a brief summary of our evaluation results and finally conclude. So let's get started with the introduction of HTAP systems. So recently, in many different application domains, there has been an explosive interest in performing analytics on the most recent version of the data, doing real time. So here we have an example of self-driving cars, which is one example of such application that require computing data while the data is being produced. So self-driving cars ingest a large volume of data from various sensors during the run of the car. And typically there is some form of learning model running the car itself or in the cloud that needs to apply decisions based on the real-time data that has been collected. Other applications that require real-time data analysis includes fraud detection, personalized recommendations, and also healthcare monitoring. Therefore, for these applications, it's critical to perform data analytics in the most recent version of the data, since the value of the data diminishes over time. So traditionally, database management systems use two separate systems to perform transactions and analytical over some data. This creates an issue since data migration between transactional and analytical database management systems can take from hours to days, depending on the volume of data. To solve this issue and support real-time data analysis, ParallelWorks have proposed the design of a hybrid transactional and analytical system. As the name indicates, such a system has the ability to perform both transactional and analytics concurrently. So in order to allow for real-time data analysis, our H-step system should provide three properties. So the first one is that H-step system needs to provide workload-specific optimizations, meaning that both transactional and analytical workloads must benefit from their own specific optimizations. The second one is that the H-step system needs to guarantee that analytical workload access the most up-to-date version of the data while ensuring the consistent view of the data in the entire system. And the third one is that the latency and throughput of transactional and analytical workloads should be as if they are running in isolation. However, as I'm going to show next, it is really challenging to achieve all of those three H-step properties concurrently for a given H-step system. So next, I'm going to talk more about the limitations of state-of-the-art H-step systems. So we studied two major types of H-step systems. So the first one is called a single instance design, where both analytics and transactional workloads run on a single copy of the data. And then we also have the multiple instance design, where each workload which workload runs on different copies of the data. So transactional workloads run on some copy of the data, while analytical workloads running a different copy of the data. So we find that neither type can achieve all of the three desired H-step properties. Specifically, we observed that the two tricky problems for both designs. The first one is that data freshening inconsistent mechanisms on state-of-the-art H-step systems are costly to implement and cause a drastic reduction in both transactional and analytical throughput. And the second one is that H-step system fails to provide performance isolation because of the higher contention at the main memory. Next, I'm going to show the limitations of state-of-the-art systems in more details. We start with the single instance design. So one of the major problems with the single instance design is the high cost of maintaining data consistency. So there are two main mechanisms to maintain data consistency in a single instance H-step system. The first consistent mechanism is called snapshotting. During snapshotting, when a transactional update happens, the H-step system creates a copy of the transactional data and send it to the analytical replica. Snapshotting happens every time a transactional workload update a row or a tuple in a column in the main replica. The second consistent mechanism is called multi-versioning concurrency control, or MVCC. In MVCC, instead of replacing the old data in a tuple when updates happen, as it's in the snapshotting approach, the system creates a new time-stamped version of the data that is chained together with the old version of the data, forming a pointer-based version change. During the execution, instead of reading a separate snapshot, analytical query can simply use a timestamp to read the most up-to-date version of the data at the time the query starts. We evaluate the impact of snapshotting and MVCC on transactional and analytical workloads. So this plot here shows the impact of snapshotting on the throughput of transactional workloads for a very number of analytical queries. We compare the snapshotting-based system against a hypothetical system where snapshotting has zero cost. We observe that transactional throughput reduces by up to 75% when increasing the number of analytical queries. The main source of throughput loss comes from the cost of executing the memory copying operation required during the snapshotting execution, which generates a large amount of data movement. Next, we evaluate the impact of MVCC on the analytical throughput for varied numbers of transactions. We normalize the analytical throughput to the system where executing MVCC has zero cost. We observe that the analytical throughput loss of up to 42% when employing MVCC. And such throughput loss comes from the fact that MVCC requires traversing long version data chains when MVCC needs to execute, which leads to expensive timestamp comparison operations and also a large number of random memory access, which can be extremely costly. Next, we study the drawbacks of a multiple instant H-step system. So a major challenge faced by multiple instant H-step systems is how to keep analytical replica up to date. In order to maintain data freshness, multiple instance H-step systems perform an operation called update propagation, which is divided into two steps. In the first step, the system needs to perform the update gather and shipping operation, which collect updates from transactional threads and send them to the analytical replica. Second, the system needs to perform the necessary format conversions between transactional and analytical data. So we evaluate the cost of update propagation in a multiple instance system. So here in this plot, we evaluate the transactional throughput from varying numbers of transactions and also update read ratios. We compare the transactional throughput of a system where the update propagation has zero cost with a system that performs only update gathering and shipping and a system that performs the entire update propagation process. We observe that from the figure that the transactional throughput reduces by up to 21.2% during the update gather and ship process, and further reduces to 42.2% during the update application process. We conclude our analysis by identifying three major limitations of state-of-the-art H-step systems. First, they do not meet all of the desired H-step properties, failing to provide high data freshness and data consistency, performance isolation, and workload-specific optimizations at the same time. Second, data freshness and data consistent mechanisms suffer from data movement overhead and are highly data intensive, leading to a reduction in transactional and analytical throughput. Third, the system fails to provide performance isolation due to the high contention in main memory. Based on that, our goal in this work is to take advantage of custom algorithms and hardware to address such limitations of current state-of-the-art H-step systems. Next, I'm going to give an overview of our proposal, which is called Polynesia. The key idea behind our mechanism is to partition the computing resources in two types of isolated and tailored processing islands, where each island is dedicated to either transactional or analytical workloads. By isolating transactional workloads using transactional islands from analytical workloads using analytical islands, we can apply workload-specific optimization to each island, avoid high memory contention, and also we can design efficient data freshness and data consistency mechanisms while maintaining data movement overhead at low cost. So Polynesia leverages processing memory techniques to reduce the data movement caused by data freshness and data consistent mechanisms. Processing memory can mitigate such overheads by adding computing units near or inside the memory device. In this case, we are going to use a 3D stack memory device. So based on the concept of process islands, we propose Polynesia, a hardware software co-designed H-step system. Polynesia includes tailored transaction and analytical islands that include a replica of the data, optimized execution engines, and a set of specialized hardware resources. Next, I'm going to briefly describe the main components of Polynesia. So first, we have the transactional islands, which includes an execution engine tailored for transactions and a replica of the data. The transactional islands is designed to sustain high transaction update rates that it uses conventional multi-core CPU systems with a deep cache hierarchy, since transactional workloads benefit from such CPU organization. Second, the analytical islands is implemented inside the logic layer of a 3D stack memory, as depicted here in the picture. So the 3D stack memory connects layers of DRAM banks with a layer of logic using high throughput through silicon vias or TSVs. The vertical partitions of a 3D stack memory is called a vault, and we place hardware resources inside each vault of the 3D stack memory, including an execution engine tailored for analytics and a replica of the data. The analytical island is designed to provide high read throughput. Thus, the analytical islands leverage simpler processing memory cores that can mitigate the data movement caused during the analytical processing. We co-design algorithms and hardware units that can efficiently maintain data consistency and data freshness in your analytical islands. Next, I'm going to describe the design of our consistency and data freshness mechanisms in details. So we are going to start with the update propagation mechanism. So recall that to maintain data freshness, the eight-step system is to first gather updates from the transactional thread and ship those updates to the analytical thread and apply those updates to the analytical replica, thus applying the necessary format conversions between transactional data and analytical data. So first, we start with our update gathering and shipping process. Our update gathering and shipping algorithm has three major steps. First, for each thread in the transactional engine, Polynesia stores an order update log for the queries performed by the transactional thread. The first stage is to scan the per-thread update logs and merge them into a single final log, where all the updates are sorted by their commit ID. The second stage is to find the location of the corresponding column in the analytical replica associated with each update log entry. You observe that this stage is one of the major bottlenecks of the update shipping because the fields on each tuple in the transactional islands are distributed across different columns in the analytical islands. Since the column size is typically very large, finding the location for each updating is very time-consuming. To overcome this, we maintain a hash index of the data on the column row key, and we use that to find the corresponding column for each update in the final log. The final stage is to ship these updates for each column to the analytical replica. We observe that the second and third step of our algorithm generates a large amount of data movement and account for 87% of the total algorithm's execution time. In order to accelerate our update gathering and shipping algorithm, we designed a new hardware accelerator called the update gathering and shipping unit. Our accelerator has three main building blocks. So the first, we have the merging unit, which is responsible to scan the update logs from the transactional thread and merge them into a single final update. To do so, the merging unit uses a three-level comparator tree. Second, it has a hash lookup unit, which is responsible to find the column location in the analytical replica for a particular transaction update in the final log. To do so, the hash lookup decouples hash computation from a hash bucket traversaling using a front-end FSM engine, probe unit, and a reorder buffer. This allows to issue concurrently hash lookups, thus maximizing the memory bandwidth utilization. Third, it has a cop unit, which uses read and write comments to fetch the hash bucket from a memory and also to send transactional updates to the analytical replica. The cop unit has multiple fetch and write back units, which allows to issue multiple memory access concurrently. Next, we describe the overall idea behind the update application process that we implement. Its main goal is to perform format conversions and apply updates to the analytical replica. Transactional analytical workloads benefit from different data layouts due to the respective computation patterns. In your relational database, the transactional workloads store data using a row-wide format, where each row represents an entry in the database and each column represents different features in the database. On the other hand, the analytical workloads store data in a compressed column-wide format, where each column stores several entries for a given feature in the database. In order to apply the transaction updates to the analytical replica, the system needs to first convert the data from the row-wide format to the column-wide format and also reconstruct and recompress the column dictionary used for the compression of the analytical replica. Next, we describe our update application algorithm, which is designed taking into account the process memory characteristics and constraints. Our algorithm initially builds a sorted dictionary for only the update. Once the dictionary is constructed, we now have two sorted dictionaries, the old dictionary and the updated dictionary. Then we merge those two dictionaries into a single dictionary using a linear scan operation. We maintain a hash index that links the old encoded values in the column to the new encoded values. This avoids the need to decompress the column and add updates, eliminating the data movement and random access while reducing the number of dictionary lookups required. Finally, we construct the new compressed column by using a hash index and the new dictionary to find the new encoded values for each entry in the column. We designed a hardware implementation of our algorithm called the update application unit and added to each in-memory analytical island. The unit consists of three main building blocks. First, we have a sort unit that uses a 124 value bitonic sorter, whose basic building block is a network of comparators. These comparators are used to form a bitonic sequence where the first half of the sequence is monolithically increasing and the second half is monolithically decreasing. Second, we use a hash lookup unit to parallelize the column compression properties. So this hash unit has a similar design as the hash lookup unit in our update gather and shipping unit. And finally, we have a merge unit to merge the old update values in the old dictionary to the new update values in the new dictionary. Our merge unit also have a similar design as that one in our update gather and shipping unit. Oh, sorry. Next, I'm going to describe our consistency mechanism. So our consistency mechanism relies on a combination of snapshotting and versioning to provide data consistency for analytical queries. For each column in the analytical replica, there is a chain of snapshot where each chain entry corresponds to a version of a column. Differently from snapshotting, Polynesia does not create a snapshot every time a column is updated. Instead, Polynesia first marks the column as dirty, and then Polynesia creates a snapshot for a column if there are any dirty columns and no current snapshot exists for a particular column. In this way, Polynesia avoids long version chains as in the MVCC approach. To accelerate our algorithm, we employ a hardware accelerator that can do fast memory copying operations, which is similar to the copy unit we designed for the update propagation unit. The copy unit has a multiple fetch and write back units to issue concurrent memory access to main memory, a tracking buffer to track outstanding reads from DRAM, and also triggering writes as soon as reads arrive back from DRAM, and a hash index used to accelerate the read lookups into the trash that needs to go into the tracking buffer. Finally, I'm going to describe our analytical engine. So efficiently executing analytical queries depends on three main design decisions. So the first one is how to do data layout and data placement of the analytical data, how to do task scheduling of analytical threads, and how to map the physical operators as scan and merge into these analytical execution engines. As prior works have shown, the execution of physical operators of the analytical queries can be accelerated by using process memory techniques. However, process memory performance is going to be suboptimal without proper data placement and task scheduling that avoids process memory constraints. Thus, we design novel data placement and task scheduling policies for our analytical engine. So I'm going to describe our data placement strategy next. The main problem related to data placement is how to partition analytical data across the varying number of vaults in the 3D stack memory, since that is going to impact the bandwidth available for the analytical replica and also the area and power available for the PIM cores for the particular analytical engine. So let's assume, for example, that we want to partition 4 different analytical columns into 4 vaults in our 2D stack memory. So there are three main approaches to do so. So the first approach is to locally partition each column to each vault, to partition each column to a single vault. Thus, a column is going to be entirely contained in a single vault. However, since each vault has a fixed area and power budget and contributes to a fraction of the total memory bandwidth of the 3D stack memory, this approach limits the area, power, and bandwidth available to the analytical engine inside a single vault. Second, we can distribute all of the columns across all of the vaults. However, this approach can lead to inter-vault communication, which increases the memory access latency and reduces memory bandwidth. Third, we propose a hybrid approach. This hybrid approach creates groups of vaults, which call vault groups, and place the columns across a single vault groups. This approach increases the available bandwidth, area, and power compared to the local approach and reduces inter-vault communication overheads compared to the distributed approach. So we invite you to check our paper for more details on our analytical engine design, including our test scheduling policy, heuristics that uses a pool-based test assignment strategy, and how we execute physical operators inside our analytical engine using a top-down volcano execution model. All of this in your paper. Next, I'm going to show a brief overview of evaluation results of Polynesia. So in order to implement Polynesia, we adapt previous transaction and analytical engines with our new consistency and data freshening algorithms. We use the Gen 5 architecture simulator to simulate the hardware component of Polynesia. We open source Polynesia in the GitHub linked in this presentation. So we compare Polynesia against a single instance system with snapshotting, a single instance system with MVCC, a multiple instance system with Polynesia's dual algorithm, and a high memory bandwidth memory, and also an ideal system where transactional workloads run in isolation. So we evaluated transaction and analytical throughput for different number of transactions, normalized to the ideal transactional system. So we make the following observations. So first, why the single instance with MVCC system is the best baseline for transactional throughput? It degrades analytical throughput by 63.2% due to a lack of workload-specific optimizations and efficient consistency mechanism. Second, Polynesia can provide 91.6% of the transactional throughput of the ideal system due to its custom processing memory logic for data freshness and consistency, and also a reduction in resource consumption at the main memory, and also a reduction in data movement traffic. Third, even though the multiple instance system with high bandwidth memory is the best software-only baseline, it still provides low analytical throughput compared to the ideal system due to high contention at the main memory. Polynesia improves analytical throughput compared to the multiple instance system with high memory bandwidth by 63.8%, which is due to a reduction on data movement supported by our custom hardware units. To conclude, Polynesia provides 1.7 times the transactional and 3.74 times the analytical throughput for prior state-of-the-art H-step systems, while achieving all of the three desired H-step properties. We evaluate the energy consumed by Polynesia for our baseline systems when executing transactional and analytical workloads. So here in this plot, we broke down the execution and the energies consumed by varying components of the system, including CPU, caches, interconnect, and DRAM. So we observe that Polynesia consumes only 0.4 times, 0.38 times, and 0.5 times the energy of a single instance systems with snapshotting, the single instance system with MVCC, and the multiple instance system. This happens because Polynesia reduces a large fraction of the power-hungry of chip DRAM accesses. So we conclude that Polynesia is an energy efficient H-step system, reducing energy consumption by 48% on average across all of the prior works. So I invite you to check our paper to more evaluations, including real-world workloads analysis, which TIP-C and TIP-C8 workloads, the effect of our update propagation and consistency mechanisms, the effect of our analytical engine design, and how Polynesia performs when increase the data set size, and also our area analysis of Polynesia. All of that is in our paper. Next, I'm going to conclude this talk. So, as we saw in this presentation, many applications today need to perform real-time data analysis, meaning that they need to execute data analysis with the most recent version of the data. Such applications often use a hybrid transaction analytical processing system or a H-step system. Ideal H-step system should provide three key properties. First, it should provide data freshness and data consistency. Second, should allow for workload-specific optimizations. And third, it should provide performance isolation to transaction and analytical workloads. We extensively have analyzed state-of-the-art H-step systems, and we observed that they failed to achieve all of the three desired H-step properties. Our key idea to solve such an issue is to divide the H-step system into processing islands, one for transaction and another for analytical workloads. Each island has a set of optimized hardware resources and algorithms. By enabling processing islands, we can perform workload-specific optimizations to transaction and analytical workloads while providing performance isolation. We leverage our key idea to implement Polynesia, another hardware software co-design HTTP system that implement custom algorithms and hardware to reduce the cost of maintaining data freshness and consistency in HTTP systems, and exploit processing memory to alleviate the data movement caused by analytical workloads. We extensively evaluate Polynesia against 3 state-of-the-art HTTP systems, and we observe that it increases transaction analytical throughput by 1.7 times and also 3.7 times on average, and reduces energy consumption by 48%. So that's all, and thanks for listening. So you can check Polynesia in the QR code in the screen. Thanks a lot. So thanks, Juan. I think my screen was a little bit stuck for some time.
Yeah, sometimes, but your voice was fine. I think your voice was fine all the time.
Yeah, something's off with my computer today. Sorry about that for the audience.
Not a problem. Yeah, Geraldo, thank you very much for the talk. We have one question from the audience. It's related to the term cost. What do you mean when you said cost in the beginning? Are you talking about monetary cost or maybe the data movement overhead?
Is more cost in terms of performance and data movement, performance and energy, rather than the costs related to monetary costs or area costs. So maybe I was talking about this in the executive summary somewhere over here. So yeah, so it's those two type of costs, like performance related and energy related costs. By doing hardware software co-design, we can further reduce the area costs compared to prior works, but it's not the same cost that I was talking about when I was motivating the need of this hardware software co-design.
Okay, well, I think that the energy cost has a direct impact in the monetary cost, right?
Yeah. So if you think about it, like if you have more area silicon in your system, you need to it's going to consume some power, right? So that is also related to the energy in the end. So in the end is everything's connected, and the performance is also related to the energy. So
makes sense. Okay. Yeah, I have a couple of questions as well. And you introduced snapshotting and MVCC, and one of the things that you mentioned is that they have a lot of data movement overhead, right, due to this memcopy operation. That I assume that this memcopy operation is handled by the copy unit in the that the transactional islands have. But I was thinking, would it be possible to do this? So not having a specialized unit for these copy operations, but instead use some of the processing using memory techniques that we have discussed in this course, and also others that we have not discussed in detail. I'm talking about RowClone, Lisa, Figaro, and these kind of proposals.
Yeah, I think that will be possible. So the granularity of the copy operation might depending on the load of the database and how. So it might be non-trivial to employ something like RowClone, for example, because RowClone copies are completely raw, right? 8 kilobytes of data from one row in a subarray to another row in a subarray, right? And for just revising to those that are not aware of those techniques. And so it's the entire row. So the mechanism would need some either software approach or some way to that make sure that the placement of the data is well laid out inside the memory of the for the analytical replica, and so we can do this communication nicely from copy from one place to the other. But definitely that could be possible for sure, and probably would even provide higher throughput than our copy unit ourselves, because the throughput of like subarray copying of RowClone is quite high.
Yeah, and also save area, right?
Save the area.
In the logic layer.
Yeah.
Okay, you have a very nice slide that introduces the two islands, the transactional island and the analytical island. And in that slide, I think, yeah, it's exactly this one. So you mentioned here that the transaction island has a replica of the data. Where does this replica reside?
So all of the data from both transactional analytical islands is sitting in main memory. The main difference when I say replica, you can think about like, let's say they have pages. Let's say there are some set of pages in main memory, like from pages in the operating system aspect of it. So there are some area that is allocated for the transactional area island, and some pages that are allocated for the analytical island. But both pages, they are sitting together in the same physical memory device. So it's not another memory or something like that. So this is a good catch. The terminology might be confusing in this case.
Mm-hmm. I see. I understand. So another question I have here is, so the transactional engines are essentially CPUs, right? CPU cores. Are they, what type of cores did you use for this work? Is x86, ARM, what type of cores?
So those are regular 86 cores with like private L1, L2, and shared L3 caches. We use those cores because a transactional, like there are many prior works in the literature showing that transactional workloads has a lot of locality when they are running updates. So as we know, to exploit locality is really good to have like caches, and also the out of order execution model of the host cores also helps. So this is why we decide to design the transactional engine, which basically regular CPU cores. But the analytical workloads have different properties that are better suited for simple cores, because here I'm just analytical islands. You can think about them about just like reading a bunch of data and processing some really simple computation based on that. So in that case, there's not much locality. Like you don't need the whole like front end decoding part of the out of order engine. So and you also, there is not much locality because of there's not much communication across different analytical queries. So
okay, makes sense. But I mean, any other device that you think that, or any other say execution paradigm that you think that could work well here? So according to, I mean, based on your explanation, I could understand that something like a GPU won't be so efficient in the transactional island.
So there is actually a bunch of work in the literature that tries to port transactional workload into GPUs actually, because like a GPU can maintain a really high throughput update rate. So it's a non-trivial thing. There are a bunch of, like, as I said, research papers about that. But prior to Polynesia, what we saw, there are some other works that propose to do some hardware software co-design somehow for step systems, not necessarily as we do, but some sort of like hardware acceleration. And a bunch of them like leverage the GPU as one like hardware components of the system. So like this could be a different execution engine, for example. And there are other related, on the other X spectrum, there are like for analytical islands, if I recall correctly, there were some FPGA related papers that tries to design the analytical islands over there on FPGAs. Analytical engine.
Yeah, I think that makes sense as well. Okay, well then, related to the this update propagation mechanism, right? So you presented the update gathering and shipping unit and the update application unit, and if I'm not wrong, both of them use hash lookup unit and merge unit. Yes. So the question here is, are they sharing? Are these, let's say, these two functions sharing the same units, or they are replicated?
So they are not shared, they are replicated, because this update propagation mechanism kind of working like in a pipeline manner, like not necessarily pipeline, but the output of one engine is the input of the other one. and like there is a flow that needs to be respected. So if you use a single engine, you are going to create a bottleneck during the whole process. So in the end, we have two engines. And I didn't mention in the presentation, but actually the design of the engines are a little bit different. So here is the update gathering and shipping. And here we have, for example, this reorder buffer here that is really important to maintain the throughput of the hash lookups for update gathering and shipping. But for update applications, we don't need the reorder, that out of order execution over here. Because here in the update application, we are not looking at all of the possible possibilities of locations of a transaction updates in an analytical replica, which the space is really large. This is why we need to do hash lookups super fast and maintain a high throughput. Over here, you are using this hash unit only for compressed two dictionaries. So the number of, even though this is still can be a bottleneck, but the space is much limited. So we don't need to maintain such a high hash lookup throughput over here. So we simplify the hardware a little bit.
And you can save this reorder buffer.
Yeah.
Okay, sounds great. Yeah, I have one last question. I don't see other questions in the chat. If someone still has any questions, please let us know. In the meantime, just my last question is related to the results, the evaluation, because I saw that you compared the throughput of Polynesia for transactions to an ideal reference, right? But I think that's not the case for the analytical. Is there any reason for that, or so? It's exactly this is like.
Yes. So we like, because those are two different metrics, right? And we want to keep like one normalized metric across all of the evaluations. So we kept like analytical throughput as like a baseline for us to compare. But like we could have done, like we could also have like ideal transaction, ideal analytical, for example, but it would overcomplicate a little bit the plot, because now you have to analyze two things that are happening at the same time with different metrics. So it's just, there's no reason. It's just like the methodology that we thought that we could simplify the explanations.
I see. Okay. Yeah. Thank you, Geraldo.
Thanks a lot, Juan. And thanks everyone for listening.
I don't have any other questions for you, and also don't see any other questions in the chat. Thank you very much, everyone.